The next section is deep learning for forecasting. So what we do in forecasting in the deep learning space is usually that we adapt the most recent NLP research, so natural language processing research, be it LSTMs, be it attention, be it transformers, be it pre-trained transformers, GPTs. We adapt that to the time series use case. And then the question is, well, what are the main differences to NLP? So usually in forecasting, the most recent observations are the most important ones. The only exception might be seasonality. And the long-term dependencies are relatively simple and stable. So only seasonalities, daily, weekly, yearly seasonalities. So in that sense, often the architectures need to be made a bit more simple. So they need to be a bit simplified. But on the other hand, so we have much more noise and uncertainty in forecasting and also much less publicly available training data. So just this first point again, right? So in NLP, not always, the end of a sentence is the most important part of the sentence. So it depends a lot on the language, on the sentence structure, where you then need to be looking for what is important. And that is what attention does for you. And then one thing that we see often is that attention mechanisms, often they kind of just rediscover the seasonality in the series that you would have known already anyway. So for example, the winning method of them for the ES-RNN that used attention only on the non-seasonal series, on yearly series, because exactly of that reason, so that for the series that have seasonality, the attention would just rediscover that seasonality, and you could easily put that in different ways. Okay, so yeah, let's start with recurrent neural networks. So there's an overview paper that I wrote with a PhD student. That you can look at. Recurrent neural networks, they have an internal state which allows them to memorize. So that's good, but they have problems to learn long memory. The LSTM, which is a long short-term memory network, that mitigates that to a certain extent. It turns out that they still work better in practice if used with an input and an output window, because the idea could be that if I now have a state, I let the state do everything. So I feed in one data point at a time and I get out one forecast at a time. But it turns out that it's still better to give them input and output windows. In that way, you make them effectively more autoregressive. And you make the state less important, but they work better. It's also interesting that some literature suggests that in general RNNs that can be trained and are stable can be well approximated by feed-forward networks. So yeah, if you think about it, an RNN is obviously a very kind of compelling and powerful model class. But if you cannot train them in a stable way, then what's the point of having this model class? And now there's this research that argues, well, you can only kind of train well a subset of the RNNs. And that subset you also can just approximate it easily by feed-forward networks, so you don't really need RNNs. Okay, let's look at the convolutional neural networks. So again, some results suggest that CNNs work just as well as the RNNs for forecasting, but are a lot faster to train. There's WaveNet, which does causal convolutions and dilations. So the name causal convolution is a bit misleading. So the idea is just that you have kind of your window, and like usually the way that these convolution kernels work is that they provide you a result for the middle of the window, whereas in forecasting we don't have that. In forecasting we need to use past data, so for us the window needs to look like this. So in order to to get an output for this data point, we can use only past data. And that's what is called a causal convolution. So there's nothing causal here. It's just like earlier in time. And dilations now just means that you leave holes in your window, right? So again, that's a way to model seasonality. So for example, maybe you want to look, it's important to look 12 data points back on a monthly series, but there's really not much of a point of looking 8 values back, right? So you look back maybe 1, 2, 3, 4 values, and then 11, 12, 13. CNNs don't have a state, so the windowing needs to cover everything that you want to use for the forecasting. And that means that often you need to use quite long input windows, especially with dilations, right? If you think about, you want to model, you have a daily time series, you want to model a yearly seasonality with a CNN, then your input window needs to cover that and be at least 365 data points long. I mean, of course, you can then also use Fourier terms and so on. So, but at least in principle, that's the idea. And what that makes is that there are some situations where RNNs really work, are still quite preferable. Namely, if input windows need to be small, right? Because then you still have the state that can remember something outside of the input window, and so that's good. So for example, if you train a global model on series with very different length, right? So let's say you have a problem where you say, I'm going to model household energy consumption. So now you have some households where you have 10 years of data, you have households where you have 3 years of data, and you have households where the people just moved in and you have 2 weeks of data. So now how do you train all of that with a CNN? You need to find one window length that fits for all of them. Whereas with an RNN, you can say, okay, well, we use a window length of a small one, 1 week, but then the state can do the rest. And with CNNs, I mean, of course, you can do padding and so on, but yeah, so in these situations, RNNs can be preferable. And still true with transformers, right? So they also need to fix an input window length. Okay, so speaking about some specialized architectures in that RNN, CNN space, there's obviously DeepAR, a very one of the first proposals in that space. That's a generative RNN model. We have the deep state space models that parameterize a linear state space model with an RNN. Deep factor models that combine a local probabilistic model with a global time series. Model that is a linear combination of factors. And then NBeats that decomposes series into basis functions and does residual stacking. NBeats is well known because it claimed state-of-the-art accuracy on the M4 after the M4, and it was also part of the second place solution in the M5 as part of an ensemble